Maar we beginnen nu met de serie De Sterren. Sommige culturen aanbidden hem als een god. Zeker is dat we afhankelijk van hem zijn. Van die almachtige zon, onze eigen ster.
We find sun temples of one kind or another. Mysterious monoliths like these at Stonehenge date back thousands of years to a time when people were totally dependent on the sun's movements. With these stones, they could track the sun's motion throughout the year and predict the coming of the life-giving spring. It's little wonder that the sun has always been worshipped as the most powerful of all gods. It gives us warmth, it gives us food, and it gives us life.
There's no doubt that worship of the sun is buried deep in our psyche, although today we tend to prostrate ourselves on beaches rather than on temple floors. In these cost-conscious, straitened times, though, we worship the sun for a different reason, as an unlimited source of free power. Today, you can get more or less solar-powered everythings. Solar-powered electricity, sun-powered houses, even solar-powered cars. And of course, most people today have got one of these little gadgets, a solar-powered calculator, which relies for its power on an array of solar cells just here.
What we tend to forget is that virtually all the energy we use on Earth is solar power. The wind and the waves are powered by the sun heating the Earth's atmosphere. And even the fossil fuels we burn are stored solar energy from the distant past. Hundreds of millions of years ago, when the Earth's climate was warmer, vast humid jungles like this flourished all over the world. The trees and plants were solar powered. They converted sunlight into energy to make them grow. After they died, the decaying vegetation was buried and gradually petrified to become seams of stored energy. Today, we extract this primordial sunshine as coal and oil.
Even more relevant is the fact that you and I are sun-powered too. When you think about it, if it wasn't for the sun, plants like these in the rainforest wouldn't be able to grow. And if the plants couldn't grow, then birds and animals would find nothing to eat. And if trees and birds and animals and plants couldn't survive, what would happen to us? Life on this planet has existed for almost 4 billion years. And over this period, all the life forms have developed an incredibly complex ecological balance. This balance ensures that no one species becomes over-dominant over the others, eventually annihilating them and leading to its own demise in the long run. But this balance depends critically on the sun's constancy. If the sun's output of energy were to change, all of this harmony would go. At best, a few species might adapt to the new conditions and survive, and we wouldn't necessarily be amongst them. If the very worst were to happen, the Earth would be baked or frozen, and every life form would be completely wiped out.
So, even though there's not a lot we can do about it, it's of more than just academic interest to know what it is that controls the sun's energy, what ultimately powers our own local star. Last century, astronomers succeeded in taking the sun's temperature for the first time, and they worked out it was 6,000 degrees Celsius. They hazarded a few guesses as to what its power source could be. Coal was was suggested because at that time it was the most powerful natural fuel known to man. But they soon realized that even if the whole sun was made of coal, it would burn itself out in just 6,000 years. The next suggestion was that the sun is powered by a continuous rain of meteorites bombarding its surface. But again, there just aren't enough meteorites around. And then they all hit on the idea that the sun is actually shrinking. The effect of compression might keep it hot for millions of years. But you need have no fear that the sun is going to shrivel up. It is fueled instead by a far more impressive power. The power of the atom. This is the rather primitive way we have been able to unleash the energy of the atom, by splitting up huge heavy atoms like uranium. Atom smashing is still the way in which we generate our nuclear power today. But this process of nuclear fission is messy. It leaves behind dangerous radioactive waste. The sun has a far cleaner, more efficient way to harness the power of the atom, by welding atoms together instead of blasting them apart. Here, at the JET project in Oxfordshire, physicists are hard at work trying to duplicate the processes which have been going on in the sun for the past 5 billion years.
Inside this incredible machine, scientists are experimenting with fusion power. What they're attempting to do is to weld together atoms of hydrogen, which is the simplest element in the universe. For just seconds at a time, the gas can reach temperatures of literally millions of degrees. But even so, we haven't yet achieved fusion on Earth. But one day, in the future, the descendants of JET will be able to provide us with almost unlimited power.
But no matter how much energy we can produce, it will always be rather puny when compared to the power of the sun, which converts 4 million tons of itself into energy every single second. Our sun is a ball of hydrogen gas so vast you could fit 1 million Earths inside it. Its nuclear reactor is buried deep inside, right at the sun's core. Only there is the gas dense enough, and hot enough at 14 million degrees, to sustain nuclear fusion. The energy from those reactions then has a long, long way to go before it can get out. It starts off as a blast of searing gamma radiation. And on the way to the surface, the gamma rays suffer countless collisions with the sun's gases and gradually lose their oomph. 500,000 years later, they have lost so much energy that they emerge from the surface as light and heat. Even so, the sun's surface is an awesome sight. Great columns of gas rise and fall, like bubbles in a boiling cauldron. That amazing film was made here at the Special Solar Observatory on Big Bear Lake in the mountains of California. This observatory is bang in the middle of the lake, but not for scenic reasons. The lake, even when it's frozen, keeps the temperature steady, and this smooths the airflow over the dome. And that means the astronomers inside can get the steadiest possible pictures of the surface of our sun. The Big Bear Solar Telescope tracks the sun with great accuracy across the sky. The cloudless Californian weather, combined with the surrounding water, make for perfect pictures. Film cameras click into action every few seconds and keep a constant record of the ever-changing surface of the sun, hour by hour. There is no other star in the universe that will ever be able to study in such detail. You need a complex telescope if you want to get good quality pictures. But if you just want to see the major changes on the sun, then you can do it with surprising simplicity.
The safest way to view the sun is to project its plentiful light through a lens onto a piece of white paper. And there you can see the whole disk of the sun projected in the field of view. It's wobbling around the edge, but that's not actually caused by the sun's own seething and churning. That's simply an effect of the upper atmosphere moving across the sun and making it appear to move. But there are are places on the sun's surface where the natural bubbling is interrupted, as if being held back by some kind of force. And that's where it cools from around about 6,000 degrees Celsius over the whole of the sun's disk, down to a mere 4,500 degrees. And as a result of this cooling, the sun's surface darkens. And you can see where this has happened on this image here. Just here, 2 here, and 3 across here. These patches are called sunspots. Now, they might look pretty puny on this scale of the sun, but that all goes to show just how big the sun is. For instance, these spots around the edge of the sun here, this whole area covers a region about 10 times the area of the Earth. Well, this is just for starters. When you use a telescope of any size, like the big one above me, you can really look at those spots in detail. If you watch them for just a few hours, they seem unchanging. But with a highly speeded up film, you notice how the spots move. Astronomers discovered that the movement is caused by the sun rotating on its axis once every 25 days. Sunspots can grow or shrink and sometimes break apart or join together. Most spots last only a few days, but some have lasted for several weeks. Andy Cameron, meanwhile, is busy back in Britain at the Royal Greenwich Observatory in Sussex, observing and modelling sunspots. His sunspots aren't on the sun, though, but on a distant star instead.
Other stars, too, have spots, and this is a very early attempt to reconstruct an image of the surface of another star which is known to have star spots. The way in which this image was obtained was using a method which is very similar to medical tomography. We use the information about how the light level of the star changes as the spots roll onto the edge and then drift across its face to reconstruct the positions and the surface brightnesses of the spots on the face of the star. And here you can see this distribution of spots. The sizes of these spots are several hundred times greater than those of the largest sunspots. The largest sunspot, as it comes onto the solar disk, maybe causes a depression in the sun's total light of a fraction of a percent. By contrast, when this complete complex of spots is on the face of this star, it's 10% fainter than when the spots are completely out of view.
On our sun, the number of spots ebbs and flows over a period of about 11 years, as you can see from this record of spot numbers over the last few centuries. In the troughs, the sun can be completely spot-free, while at the peaks there are always 1 or 2 clumps. In this century, there have been high peaks around 1960 and 1980, and another one is due in the early 90s. But what's wine got to do with all this? Well, there does seem to be a link between sunspots and our weather. And some people reckon you get the best wine vintages when the sun is at sunspot maximum. The reasoning goes that when the sun is spotty, you get warmer weather, and so you get riper grapes and better wine. Actually, there does seem to be something in this. It's been shown, for instance, that the highest number of runs at cricket occurs when the sun is at sunspot maximum, while at the same time the Scottish raspberry growers find that they get their very, very best seasons when the sun is spotty. It's all to do with the weather. On the other hand, an unspotty sun may bring cold weather. There was a very peculiar period in the late 17th century when the sun went spot-free for many years. It became so cold in England that the Thames completely froze over and people held frost fairs on it. Is there really a link? Well, it all depends what you make of the statistics. But whatever effect sunspots may or may not have on the weather, there's no doubt that their influence goes way beyond the sun's surface. Hanging above sunspots, you often find large glowing clouds called prominences. In fact, sunspots and prominences are intimately linked. They're both manifestations of the sun's strong magnetism. Great magnetic loops push up through the sun's surface and into the atmosphere above. The prominences flow down the magnetic field lines. If separate magnetic loops ever touch, you get a short circuit. The result is a gigantic explosion, a solar flare, that is millions of times more powerful than any of our nuclear bombs. The effects of these flares can be felt way beyond the sun, a long way beyond. During the last war, our vital radar defenses were jammed by radio noise. At first, we thought the Germans had a secret weapon. But the jamming source seemed to keep moving. One man was assigned to find the real culprit.
Well, we got all the reports in, they all came to me. And many had recorded the bearing, the direction of the jamming, and that it moved through the day corresponded to the direction of the sun. And two sites, too, managed to get a sort of elevation as well. And a few reports didn't fit in with this idea, but it seemed to me it was obvious. It had occurred only during the day, followed the sun. It must be radiation coming directly from the sun. So I phoned up the Royal Observatory, and they told me that there was a big sunspot. And as the sunspot's a very disturbed region with high magnetic fields and a lot of particles, electrons and protons coming out, some at various speeds, some at 1,000 kilometers, some higher speeds, cosmic rays, particles. I thought, well, why not it be a source of radio emission? And so it seemed to me quite a natural conclusion.
Eagle, we got you now. It's looking good, over. Roger, copy. Roger, you're a go to...
Half a century on, in the space age, we know Stanley Hay was right. Highly charged particles do come streaming past the Earth and Moon whenever there's sunspot activity.
Four forward.
During the American Apollo lunar landing program, these particles from the sun were taken very seriously indeed, because they do more than interfere with radar and radio. They can also be harmful to human beings.
An astronaut, like my friend here, is particularly at risk because he has no protection, no atmosphere to cushion him from the fast-moving particles that are released when the sun has an outburst. And with many new space projects coming up, like the building of new space stations and even a return to the moon contemplated, this is one aspect of crew safety where we can't take any risks at all. Fortunately, the design of spacesuits is very sophisticated indeed. This one here consists of something like 17 layers of fabric and metal weaved together, and it's very unlikely that anything from the sun could penetrate this. Meanwhile, back on the Earth, you and I need have no complaints about solar flares, except, that is, when they disrupt our favourite radio and television programmes.
But solar flares do have their compensations, and the sight of an aurora is certainly one. These are the northern lights, the aurora borealis. They're best seen near the poles. These were filmed at a research base in North Alaska. These ghostly, flickering curtains, seen moving at their real speed, are caused by charged particles called electrons that started life in solar flares. The electrons travel to Earth in what's known as the solar wind. At the poles, the Earth's magnetic field channels them downwards, so they crash into the upper atmosphere and create light. When an electron hits an oxygen molecule, green light is emitted, and if nitrogen is struck, the result is red light. The strength of the solar wind depends on how stormy the sun is and on how many sunspots it has. It can be a gentle breeze or a roaring gale. Space space probes have revealed that the solar wind stretches past the Earth to affect our whole solar system. One of the best ways of seeing the source of the solar wind is when there's a total eclipse. When the moon gets in the way and blocks off all the dazzling glare from the main part of the sun's disk. Then the sun's corona flashes into view, a pearly halo fading away into space. This video, shot at normal speed, was recorded at the 1988 total eclipse in Sumatra, Indonesia. The corona is distorted and uneven because of the sun's complex magnetic field. During this eclipse, it was even possible to see prominences. The best one is at the 11 o'clock position. But the view is all too brief before the moon moves away again. In all, this total eclipse lasted only 2 minutes. But of course, the best way to keep tabs on what the sun and its atmosphere are doing is from space. There's no air to get in the way, and so you can view the sun against a permanently black sky. Astronauts on the Skylab space station used a special X-ray telescope to photograph our sun's glowing atmosphere every day as it rotated, watching its ever-changing weather systems. This film represents 2 months in the life of our local star. But now it's also possible to keep a constant remote weather eye on the sun, day in, day out. This is done by the TELEAC satellite, famous after its dramatic rescue by space shuttle astronauts. By creating an artificial eclipse with a small disk in front of the camera, TELEAC can reveal the true extent of the corona and reveal storms as they start to gather above the sun. But other stars put our sun's tantrums to shame. Their fluctuations are so large that life would be impossible on any planet circling such a star. And some stars even appear to have changes which take place over hundreds or thousands of years.
If other stars have long-term variations, what about our local star, the Sun? Telescopes like these at the Big Bear Lake Observatory monitor the sun's surface day in, day out. But what they're looking for is just skin deep. They're not looking for long-term periodic fluctuations. If you want to measure the sun's true heartbeat, you need to use a different kind of telescope, one that's buried a mile underground. Deep down a gold mine in Dakota, physicists are using a tank of cleaning fluid to monitor reactions at the sun's core. Shielded underground from all other stray particles and radiation, they can trap highly penetrating particles called neutrinos that wing straight from the reactions in the sun's powerhouse. The number of neutrinos trapped tells how fast the reactions are proceeding. The more neutrinos, the faster the reactions, and the hotter the sun's heart is. Theoretical physicists had predicted they should pick up 1 neutrino a day from the sun. But to everyone's astonishment, the tank picked up a neutrino only once every 3 days. There seemed to be something wrong with the sun. The sun's energy takes 500,000 years to bubble from the center to the surface. Does this mean that the current low neutrino rate could be telling us that in 500,000 years' time, the sun's output of light and heat could be reduced? In which case, our descendants will suffer death by deep freeze. Experience tells us this won't be the case. The Earth's climate has changed many times during our planet's history, but these changes have never been so much that life has been wiped out. Whatever changes have happened in the sun, they've been kind so far as our own planet has been concerned. So on balance, we've been very lucky with our local star. It's served us faithfully for 5 billion years in the past, and it will continue to serve us for 5 billion years to come. But one day there'll come a change that the Earth won't be able to weather, and that will be the death of our sun. And the death of our sun will mean the death of the Earth as well. But hopefully it won't mean the death of us, because by that time, 5 billion years in the future, our descendants will be able to leave this planet and search for another home in our star city. And so perhaps, in the far, far distant future, our descendants will look into the skies of another planet, warmed by the rays of a different sun.
Ook in het boek bij deze serie staat het boeiende verhaal van de zon. Het boek is te koop bij de Nederlandse en Vlaamse boekhandel voor 44,50 of 890 francs. Bestellen kan ook. U maakt 44,50 over op Giro 54 42 32 van TELEAC in Utrecht en het boek wordt thuisbezorgd. Over het onderzoek van de zon gaat ook radioprogramma 3, woensdagmiddag om 3 uur op Radio 5. Hoe we de geheimen rond de geboorte van sterren kunnen ontrafelen, wordt uit de doeken gedaan in televisieprogramma 4. Volgende week maandag 5:05.